Welcome everyone. So for those on YouTube, this is our 15th live stream geometry session. So right now I'm here with Marin from Bulgaria, and I'm sure more people will join later. So today I chose a bunch of problems from the Japan Math Olympiad. So they usually do pretty well at the IMO. I didn't see a team selection test for them on the internet, but these problems still look pretty interesting. So that's what I went with for this week. So I'm going to share my screen. Hold on just a second. Let me find it. Can you see my screen?
Oh, yeah.
All right, so here's the first problem. So I'm going to maximize it. We have 5 points on a circle, but we know that MA is equal to MB. So I'm going to try to do it like this. So we have MA equal to MB. And they're all on a circle. So let's see. Here we go. I'll use this. Let me hide that circle. And then so they're A, M, B, C, and D. AC and MD meet at P. And whoops, AC and MD. And then BD and MC meet at Q. Those are P and Q. Call it P. Call that Q. Okay, and then it says if the line PQ meets the circle at X and Y, then we want to show MX equals MY. So that's like the same as saying that AB and XY are parallel, basically. Yeah, basically we want to show AB and PQ are parallel, right? Whoops. All right, that should do it. And we have to use that MA equals MB. Let's see. I'm going to label this point. So AB we want to show is parallel to PQ or XY. Maybe we could use like projective geometry. This feels a lot like projective geometry. Or maybe Pascal's theorem. You know what? I wonder if we could do it, yeah, using Pascal's theorem. I feel like it might be like a degenerate case or something. So let's see. You have MD and AC, MC and BD. Basically, we want to show those concur at the point at infinity. So basically, AB and the tangent line at M. So yeah, what if we did Pascal's theorem on A, M, M, B, C, D? Let's see. Yeah, I wonder if this is just Pascal's theorem. So AB and the tangent at M meet at the point at infinity. How much do you know about projective geometry?
I know Pascal's theorem.
Right. So yeah, if we like consider the like a hexagon AMM, so we like consider M twice, BCD. Does this follow from Pascal's theorem? I'm trying to think. So we have AC and MD, MC and BD, and AB and MM, basically. So if I, let's see, if I write out the 6 points, sort of like this, so I have, let's see, yeah, I'm kind of bad at applying Pascal's theorem like in a degenerate form. And then MCD or something like that. Let's see. So I think we want, let me try this. We want, let me change that to a C and that to a B.
There's actually an easier way to write Pascal's. So if we take, for example, 6 points on a circle, for example, A1, A2, A3, A4, A5, A6, then the intersections of AI, J mod 3 lie on a line. So if we take like the degenerate hexagon MMC ABD, this problem just, yeah, is solved.
Okay, so it's Pascal's theorem, but let me see if I can finish it this way, just because this is how I originally remembered it, but then I'll think about it the way you mentioned. So yeah, maybe I should swap B and C. Okay. So if I call that D and this C, then we have AB intersects MM at point at infinity on line AB. And then we have AC intersects ND at P. And we have MC intersects BD at Q, and so that would solve it. So yeah, I wonder if this is the same as, so yeah, I'll just write by Pascal's theorem, P, Q, and AB. Well, yeah. Let me add another. Just typing it out for the viewers. All right. And so let me put this in dollar signs just for the heck of it. All right. See how that looks. So by Pascal's theorem. We have P, Q, and the point at infinity. Are collinear, and that means that PQ is parallel to AB. And that means that XY is parallel to AB. Right. And that means that MX equals MY. All right. So I'm guessing this is probably equivalent to what you were thinking, right? Just written out in a different way.
Yeah, I just mentioned another way of writing it.
Yeah, because if you take it mod 3, like if you start at A and then you go like 1, 2, 3. Yeah. It has to be equivalent to this, right? Just it's like stated in a different way, kind of, right?
Yeah.
All right, sounds good. So I will move to the next problem. That was a short one. Hey, Rodrigo, thanks for joining. Good to see you, Rodrigo. Thanks for joining. So this is the second problem. So the first problem was sort of a degenerate case of Pascal's theorem. So for this problem, we have a triangle. This is kind of interesting. BD. So we have a triangle ABC. This is just this year, so 2020. Okay, I think we'll want like a tall triangle. So something like this. And then, so this is point D and that's point E. And then, I see you put a thumbs up, Rodrigo. Thanks. BE and CD meet at point P. And then we draw the circumcircles of ABE and ACD. Whoops. That's point P. Let me draw those two circumcircles. So ABE. ACD is probably going to intersect the problem, but oh well. And they meet at a point Q. And we want to show that PQ and BC are perpendicular. All right. Kind of interesting. So we have like these equality of segments. So BD equals BC equals C. So two isosceles triangles here. All right. So maybe we could show like PB squared minus PC squared is QB squared minus QC squared. Just one thought. Let's see. I'm just curious. PQ and BC are perpendicular. This is a tricky problem. Thinking if we could do like power of a point or something. Yeah, so what would that mean? There's like another way I could drop a perpendicular from Q to BC and show that those are collinear with P. I wonder, is Q the orthocenter of BPC? Huh. I think maybe Q is the orthocenter. That would mean F would be the midpoint of CD. Let me check that. I think it really might be that simple. So basically, I think we can show Q is the orthocenter of BPC. Just trying to figure out how. So let's see, this is so yeah, we want to show F as the midpoint of CD because BDC is isosceles. Is it? That's interesting. F is the midpoint of CD and G is the midpoint of BE. So that means BF has to pass through the center. But let's draw the centers of those circles. So center E, center K. Whoops. I hate it when GeoGebra does this. Center of K. So we want to show BQ passes through I and CG passes through H. Let's see. Q must be the in-center of triangle ABC. Interesting. Yeah, we want to show Q has to be the in-center of ABC. So let's see, angle BAQ is half of angle BHQ, or BAQ is the same as BEQ. It is interesting. Yeah, it feels to me like we're really close to solving it, but I just don't see immediately how to do it. Let's see. So yeah, can we show Q as the in-center? Is there some trick with like angle BQC is 90 plus angle ACB over 2? Oh, I'm sorry, angle BQA is 90 plus ACB over 2. and therefore Q has to be the incenter. Okay. Let me just think about that angle chase. Angle BQA. We can write that. See, angle ACB. Oh, I guess because angle ACB is the same as angle BEC, and then you can do an angle chase from there. Okay. So let me just think through this in my head. Yeah, so that's sort of a straightforward angle. So we know angle BQC. We know angle CQA. We know those three angles. And now I'm just trying to see how does that force it to be in the center once we know that. I think it's true. So let's say we know angle BQC, CQA, and AQB, right? Let's say we know all three of those angles. How do we then use that to show that Q is the incenter? Yeah, the incenter is unique, but like maybe there's another point that has those same three angles. Well, I guess there can only be one intersection of those three circles, right? So that would prove it, right? Yeah, because if it, okay, so I'm going to write that out. Thanks both for your help. Let me shrink it a little bit, make some room. Okay. Yeah, sorry, I think this is just gonna overlap the diagram. This is similar to EGMO 2014. Interesting. All right. I'm guessing you're referring to the European Girls Math Olympiad, right? So we have angle BCA is equal to angle BEC, and which is 180 minus angle BEA. And then that is, I'm trying to think here. So 180, so we can write BEA. Wait, how did I do this? Oh, I'm sorry. We want BQA. My bad. BQA. Hold on a sec. 180 minus BEA. And that's 180 minus BQA, right? Wait, if BCA is gamma, then BEC. Oh, I was considering it isosceles the wrong way. Yeah, BCA and BC are not equal. So you're right. So so I'll write it like this. So BCA is 180 minus twice angle BEC, which is 180 minus twice angle CBE. Yeah, my bad. And I think that's right. Yeah, sorry, this is taking me a while. I'll just do it the other way, I'm sorry. So we have angle BQA equals angle BEA is equal to 180 minus angle BEC, which is equal to 180 minus half of 180 minus angle ECB. Here we go. Since okay, and then that simplifies to 90 minus half angle ACB. Oops, sorry. Okay, so BQA is 90 minus half, and then similarly CQA is 90 minus half ABC. Okay, and those same angle equalities hold true for the in-center. And so basically by uniqueness of the in-center, Q has to be the in-center. Just write by an angle chase, these two okay. Yeah, I'm not gonna write up the whole angle chase there, but so that means Q is the in-center of ABC. Now these problems are a bit easy, I feel like, but if we get through them quick, maybe I could try a different contest. All right. And once we know that, then we can show Q is the orthocenter of PVC. So BD equals BC. Right? So that means BF is perpendicular to DC. We'll just write CD. And then similarly, CG is perpendicular to BE. And so Q is the orthocenter of BPC. And so PQ is perpendicular to BC. All right, so I will move on to the next one. So yeah, I kind of didn't, but yeah, this line follows from the uniqueness, as you mentioned, the uniqueness of the incenter. All right. So let's try this one. So this one is from 2019. So I think that last one was 2020. This one looks like it, I guess I can't really tell how hard it is just by looking at it, but it's whenever you show two circles are tangent, sometimes that can be tricky. So I'm going to draw the in circle. I is the incenter. M is the midpoint of side BC. Sorry, this is driving me crazy. I'm just going to add that. Let's call that M. A line through A perpendicular to BC, and a line through M perpendicular to AI meet at K. I feel like I've seen something like this before. This looks pretty kind of familiar. So those two meet at point K. We want to show the circle with diameter AK is tangent to the end circle. It's kind of interesting. The diagram looks simple enough where it looks like it's probably not that hard, but let me draw that. There we go. And they're saying that this circle should be tangent to the end circle. That's interesting. Now, whenever I see tangent circles, like I try to find like a homophily. But yeah, it's interesting. Well, you know what? If we show the radius of the big circle minus the radius of the small circle is equal to EI, that would solve the problem, right? Because if you take EI plus the radius of the smaller circle and you get the radius of the bigger circle, that means they're tangent, right? You just have to figure out what is EI. So E is the midpoint of AK. Yeah, maybe we should reflect A over point I and see what that does. Let me try that. So A prime is the reflection of A over I. I'm not sure if that really helps. Although it means BA prime is equal to AB. I'll just delete that. I'll be right back, guys. All right, thanks for waiting. Guys have any ideas yet? So yeah, I feel like that's the most natural way to solve this, to show that EI plus the N radius is equal to AE. So we have AI times ID is EI squared minus AE squared. Yeah, I wonder, I'm kind of thinking about this algebraically. I'm going to write it on my notepad. But we have AI times ID is equal to AE squared minus EI squared. And then we have a difference of squares. Right. Yeah, we have to use somewhere that M is the midpoint of BC. So we have a cyclic quadrilateral here. It's probably worth drawing it. Oops. So IFDM is cyclic. I don't know if that helps. I wonder if it passes through the point of tangency. It kind of looks like it, right? Yeah. This is the advantage of using GeoGebra versus being in a competition, but this sure looks like that tangency point where IFDM intersects both circles. And Marin, for the problem that you sent me, I feel like it was maybe something similar too, where like the intersection, the tangency of two circles lies on another circle. Let's see. So wait, is AK perpendicular to BC? Is it obvious that AK is perpendicular to BC? We know angle ADK is 90. Oh yeah, no, by definition, AK is perpendicular to BC by how K was defined. Does EI pass through the point of tangency? Yeah, it looks like EI passes through that tangency point. Yeah, how should we think about this? I think it might be best So I'm going to hide the circle with diameter 8K. Yeah, now it's just a matter of like setting up proof. But if you let EI meet the in circle at a point, what is E? Oh, E is the midpoint of 8K. That's how I defined it. We want to show AGDK is cyclic, right? So step one is to show AGKD is cyclic, and then step two is to show that the circles are actually tangent, which I think wouldn't be that hard. Are KF and G collinear? Possibly. Let's check it out. Sure looks like it. Yes. KF and G. How do we prove that they are collinear? What if, you know what? First, I'm going to do it like this. I'm going to let this circle meet the other circle at G. And then first we want to show KF and G are collinear. Then we could try to show EI and G are collinear. I lost point A there. There we go. So can we show? So there's a bunch. We want to show KF and G are collinear. We want to show EI and G are collinear. That would mean, let's see. There's so much stuff going on, I don't even know where to start. But yeah, we want to show KF and G are collinear. We want to show EI and G are collinear. We want to show AGDK is cyclic, and we want to show that that circle is tangent to the in circle. I wonder, yeah, let's see if we can. Yeah, I think the angle IGM is 90. Yeah, first I'm trying to think how to show EI and G are collinear. I doubt it, but is I the midpoint of AB? No. Hold on just a sec. Let me check. Let me check my Discord. Hold on just a second. Oh, sorry. That wasn't for this group. Okay. Never mind. Oops. Yeah, there's just so many different things with this point G. But let me try something. I wonder if AG passes through the topmost point. I think it might. So if I take this topmost point, yeah, there's so many things going on with point G that I feel like the problem has to solve. Well, that would have to be true if we knew the rest is true. So I think, yeah, it's just kind of a matter of where to begin. So if we took the topmost point, yeah, let me try it like this. So I'm going to hide this circle, and I'm going to draw the topmost point. So hold on just a sec. So F prime is the topmost point, and I will let AF prime intersect the end circle at G. And then can we show IFMG is cyclic? So that's the same as showing MG is tangent to the end circle. And I think that's true. Yeah, because we know basically, you know, there's like, so it's well known that FM is equal to MH, right? And also we have IF is equal to IF prime. So IM is parallel to F prime H, right? And so from there, basically we can show from there it's not a hard angle. Like we just need to show IM bisects angle FIG, and then which is an angle chase, and then we have that IGM DF is cyclic. So I can prove that. I can prove that those are cyclic. Now I want to see if I can prove that EI and G are collinear. So E is the midpoint of AK and I is the midpoint of F prime F, right? We know angle F prime GF is 90 degrees. So yeah, if we could show GF and K are collinear, that would solve I think that would solve the problem. Yeah, once we know GF prime and K are collinear, it solves the problem. Or we could show EI and G are collinear. I don't even know, we might as well remove point E because showing EI and G are collinear is equivalent to showing KF and G are collinear. Whoops. Whoa. See. So do you mean this point right here? Okay, yeah. So how do we show K, F, and G are collinear? We should show A, J, F, G. A, J, F, G is cyclic. That's because it has two right angles. And then we also know A, J, D, M is cyclic. That's a lot of circles. Okay. And so then, radical axis theorem? Yeah. So that would mean A, J, D, M, and F, G are collinear. I like it. That's a nice solution. I like it. All right. So I'm going to type it up for the viewers of the channel. All right. Let me erase some of the lines that we added, and I'll add them in later. So, yeah, I'm sure this problem would have been harder without GeoGebra, but it was a fun one. Yeah, did we even need this circle? I don't know if we did. Oh yeah, I think we did need it. Okay, so yeah, for the radical axis theorem, we needed it. Whoops. So let Fi meet prime. So F prime is a diameter. All right. And let AF prime meet omega at G. And I'll say and BC at so it means omega at G, and it meets BC at H. Then so it's well known that FM is equal to MH. So I did a video on that. So see video on IM lemma. I'm not sure what number the video is, but that's what I call it at least. And then Fi is equal to IF prime. So IM is parallel to F prime H. right. Should fix that. And so from there, we can show IM as the angle bisector of FIG. So we have, just thinking how to write this out. Angle FGF prime is 90. That, yeah, so since FGF prime is 90, that means FG is perpendicular to IM. And that means MG is tangent to omega. All right. And once we know that, what else did we show? So then IFGDM is cyclic. So all right, so I'm going to draw that in. And then we also know IJDM is cyclic. Whoops. And then last, we want to show AJFG is cyclic. So angle AJF is equal to angle AGF is equal to 90. So that means AJFG is cyclic. And then we can apply the radical axis theorem. Let's draw that in. So by the radical axis theorem, AJ, FG, and EM concur at K. So that means that FG passes through K, which is, hey, Khan, thanks for joining us. So Khan's from Turkey, and he just joined us last week. And we also had Marin, who's new this week. All right, so, hello. All right, so this is our third problem. So I think it's our third, so we're going pretty fast. And then once we know that, basically, I mean, AGDK is cyclic with diameter AK, and a homophily at G takes one to the other. So that finishes this off. So all right. then, yeah, I guess I might as well draw it. F, and then F prime F is parallel to AK. A homophoty at G takes the circle F prime FG to AGK, and that means that the two circles are tangent. Let's see. All right. Yeah, I guess I'll just draw in that last circle. Why not? And then we can move on to the next problem. And you can see those two circles, F prime FG and ADK are tangent, and F prime FG is the end circle. So that solves it. Or just triangle F prime FG is similar to KAG. So GI goes through E. Ah, yeah, that also works. Yeah, I deleted point E, but that definitely also works. All right, so let's move on to the next problem. This is our fourth one already. So we have a scalene triangle. This is another one with equal segments. This is 2018. So we have a triangle ABC. CA, okay, so this time we want to do it a little differently. So CA is equal to CB and BA is equal to BE. So I want to go like this. And like this. Right? So CAD is isosceles and BAE is isosceles. Sounds good. The W is, omega is the circumcircle of ADE. All right. P is the reflection of A across BC. Okay, so I'm gonna have to make a little more room here. Actually, you know what I can do? Since P is the reflection of A across BC, then P is where those two circles intersect. Actually, I think I'm going to use unhide instead of drawing the circles twice because I already drew them, right? So let's see. I'm going to need to shrink it a little bit. So we want to see point P. So that's point P down there. So PD and PE intersect the circle again at X and Y. Okay. So that's X and that's Y. Let's rename it. This feels a lot like Pascal's theorem, I feel like. Maybe they just like doing Pascal's theorem in Japan. Sometimes certain countries like certain theorems a lot. So like Iran likes Poncelet's porism. I think Peru likes IMO shortlist 2002. So yeah, maybe Japan likes doing Pascal's theorem. Let's see. But yeah, that's what it feels like. Maybe it doesn't work. I don't know. Oh wait, hold on a sec. Oh, yeah, it looked a little weird, but okay. So let me unhide A. Yeah, it's hard to get a good figure here, but we want to show BX and CY intersect on the circle. How do I make this look a little better? That looks good in my opinion. All right. Oops. So maybe spiral similarities or something. Let's see. Or Pascal's theorem. So what would that mean if they did intersect on the circle? That would AXB and AYC. Oh, kind of like a spiral, yeah, like a spiral similarity. Yeah, that would prove it, I think, right? Whoops. Let's see. So angle AXB is 145.7, and angle AYC. Yep, so they certainly look similar. I could just check one more angle, but I'm pretty sure they are similar. And I think they'd have to be similar for the problem to be true. Yeah. So can we show AXB is similar to AYC? So that's the same as saying, so EX and DY are parallel. Huh. So I thought that was like a coincidence in the diagram I drew, but yeah. EX and DY would have to be parallel if that were true. And maybe that's just an angle chase. EX, YD, and BC. So all three of them are probably parallel. Is that obvious? Let me check. Does PE equal PX? Yeah. PE equals PX, PD equals PY. Also, BDCE is cyclic. Yeah, that's true by an angle chase. Yeah, I didn't even realize those two isosceles triangles are similar, but that is true because those two isosceles triangles are similar by an easy, and P lies on it also. Isn't GeoGebra great? It just gives us the answers to everything. But yeah, that would just be an angle chase to show that P lies on that circle. Okay. Is it obvious? So yeah, how do we show XE, DY, and BC are parallel? So angle PXE is equal to angle DAE, and angle PEX. Yeah, it's just well, actually, I'm not sure. Yeah. ABE and ADC are similar, and we want to show I want to show AXB is equal to AYC. Yeah, how do we show that parallelism? There has to be a way to show that. So we have angle YDA is equal to angle YEA. I think it's probably just an angle chase. So YDA is equal to YEA, which is DAX. So yeah, how do we show angle DAX is equal to EAY? And then I agree we could use ratios for the rest. But yeah, I want to show that they're both parallel to BC. I want to show that angle YDA is equal to angle CBA. And I bet that's an angle chase because, yeah, we have to prove the parallel. But so YDA equals YEA is PEC, right? And PEC is PBC. Is C the midpoint of arc DP? I think so. Yeah. So is it obvious that C is the midpoint of arc DBP or arc DEP? Well, this angle ABC is equal to angle PBC. So then that solves it. Okay. So yeah, so I think we have enough to finish this. So I am going to start writing it up. Hey, Rodrigo left. Oh. All right, so I'm gonna write it out. So we have angle ADY is equal to angle AEY is equal to angle PEC, which is equal to angle PBC, which is equal to angle ABC. And so that means that DY is parallel to BC. Okay. And then similarly, EX is parallel to BC. Okay. And so since dy is parallel to EX, that means arc DX is equal to arc EY, which means that, so I'm going to write this out. So I'll say arc DX equals arc EY in the circle. Oh, but I should prove that P lies. Okay, I'll go back and do that after. Yeah, I didn't prove that P. I didn't prove that P lies on. I didn't prove that these are cyclic or that P lies on the circle yet. So I'll just make some room to prove that. But basically, I'll write it like this. So ADC and AEB are similar isosceles triangles. Since they share angle A. So that means that angle BDC equals 180 minus angle ADC, 180 minus angle AE, which is angle BEC. And so that means that BDEC is cyclic. So I'll write it out like this. So yeah, we also have angle BC is angle BAC is angle BA, which is 180 minus angle BEC. So that means all 5 of those points lie in a circle. So so BDECP is cyclic. All right, so I'm just going to fit in everything here. So that's, whoops. That is like the full proof of those beginning steps. Then, so since those two arcs are equal, that means angle BAX equals angle YE. And that means angle BAX equals angle YAC. Okay. We also have AX is equal to AE and AD is equal to, we have a bunch of equal segments here. But yeah, so let's try to use ratios. So we have AB over AX is equal to AB. Yeah, so it's just ratios from here. So AB over AX is equal to AB over AE, which is equal to AC over AD, since the triangles are similar, which is equal to AC over AY. So then ABX and ACY are similar, and then a spiral similarity takes one to the other. So yeah, I'm just thinking how to write this. So I'll just say a spiral similarity takes, or a spiral similarity of A takes triangle ABX to triangle ACY. And then that means, from properties of spiral similarities, that BX and CY concur on that circle. All right. Right. and it's also just an easy angle chase if you don't know spiral similarities. Because if a similarity takes triangle ABX to triangle ACY, then there's also one that takes ABC to AXY. So yeah, so that is it for this problem. I will move on to the next one, but yeah, we're flying through these.